You're welcome to the physics class on the topic dimensions. So, what is dimension about? Dimension is, relating a quantity to the fundamental. So, dimensions is about the relationship. It expresses the relationship between a physical quantity and then the fundamental quantities. So, you should have learned that a quantity in physics or in science, a physical quantity, it can be of any of the two types, either fundamental, you have the fundamental quantity, then we have the derived quantities. So, and the fundamental quantities, they are called they are the basic quantities. So, and the derived ones are obtained from the fundamental quantities. So that is how it takes the name derived. So the derived quantities are derived from the fundamental quantities. While the fundamental quantity, they are the basic quantity, which are derived from no other quantities. So they are the basic, the fundamental, from which other quantities are derived. And so when we try to now relate a derived quantity to the fundamental quantity from which they are derived, then we're talking about dimension. So the dimension of a quantity is its relationship to the fundamental quantities. So how related to the fundamental quantity a particular quantity is what we call dimension. So the dimension will show that, okay, this quantity, has been derived from certain fundamental quantities. So that means we need to know what the fundamental quantities are. Sorry. So, mind you, the topic is dimension. Dimension. So, like we said, the fundamental quantities, the fundamental or the basic quantities, they have the length. The length is a fundamental quantity. The mass, have time, temperature, then we have amount of electricity, let's say the electric current, then we have amount of substance. So these are, the fundamental quantities. So the length, so which measures, when talking about how long an object is, how long a dimension is, that is talking about the length. Then you have the mass, which measures the amount of substance, contained in a matter, in a substance, the amount of matter that a substance contains. They will have time, measurement of duration, the temperature measuring the degree of hotness or coldness of the substance, and electric currents measuring the flow of electrons in a conductor. You have amount of substance used in expressing the quantity of chemical species present in a molecule of it. So that is an amount of substance. So these are fundamental quantities. And these quantities, these are the names. Then there are dimensions. The dimension of length is L, capital L. That of mass is capital M. Then time is capital T. You understand? So time is capital T. Then uh, for temperature, current, and this. So we can use N for the amount of mole, then electricity is the current, so which we can use I, you understand? Then the temperature here, so we can use this for instance. So majorly the length mass time, so it's what is going to concern us with. So but for the rest temperature, you can this adjust the dimensions. These are given at the dimensions. That is the dimensions, not the unit. Yeah, the symbols of the dimension. So a length is capital L, a mass is M, and a time is capital T. Then a temperature, the absolute temperature, the temperature is theta. So you can use theta for the temperature. Then electric current I, then the amount of substance, which is, you can use N as the amount of substance. So these are then we have the units. You are not going to be much interested in the units, but if you must talk about that, the units, units have two types. You have the SI unit. There are different types of unit. Then we're talking about the SI unit, the SI unit, International System of Units. For length, length is measured in meters. Understand? It's measured in meters. And a mass in kilogram, that is kg. Then time in second with symbol S. The temperature, the absolute temperature is measured in Kelvin. In Kelvin. So, okay. You also have the degree Celsius, which is this. Then for current is ampere, symbol A. Then we have the amount of mole is mole. You understand? So amount of mole is mole. Okay. So these are the units. Why these are the dimensions? So the most important of these dimensions is LMT. So we're going to be looking at how a quantity is related to the length, the mass, time, and even any of the other fundamental quantities. Then examples of derived quantities. When you say derived quantities, then you have examples like so we are going to give examples of derived quantities. Derived quantities. The example is area. Area. Then you have volume. You have pressure. Or again, you have power, work, even energy. Then you have force and others. This speed or velocity, acceleration. So all these are examples of derived quantities. So derived quantities in the sense that they are derived from the fundamental quantities. For instance, area is derived from length. So area is just a square of a square of length. So square of length is an area, which means when you square a length, you have an area. So meaning the dimension of area is L square. For instance, the area, when you're talking about the area of a rectangle, so you calculate the area of a rectangle by multiplying this dimension length by this breadth. It's a length times breadth. So both length measured here is a measure of length. And the breadth is also measuring length. They are only taking different names. So the breadth is also a length measurement. So you're actually multiplying two lengths, giving rise to L squared. So while a volume is a cubed length, it's a length raised to power 3. So when a length is cubed, then you have a volume. An example to indicate that is when you have, for instance, a keyboard, a keyboard where you have all the sides are equal. So with let's say one side, for instance, then the volume is calculated as the cube of a side. So and a side, a particular side is a measure of length. They multiply raised to power 3. So meaning is a volume is related to length, which is the fundamental quantity, by keeping uh, the length. When the length is kept, then you have a volume. You understand? So we say that the dimension of volume is L. So the dimension of area is L square, length square. Dimension of volume is length K. So this is how volume is related to length, it's fundamental quantity. So we have for every other unit. You understand? So even if you are to look at, for instance, the area of a circle, which is pi r square. So you notice that this is a constant. Then a measure of radius is a length. Radius is a length measurement. So you have L then square. Then you ignore the constant. So this is still a proof that the dimension of area is L square. So that is that about that. So the next thing we're gonna do now is to see how to derive the dimensions of any unit given to you, just like you have done to area and volume. So how do we get the dimension of any of these quantities? So before you can get the dimension of the quantity, you should know the mathematical, expression of that quantity. What is that quantity? When we say, for instance, velocity. So what is velocity? So if you say velocity, for instance, velocity. So we say velocity mathematically is what? Distance over time. Distance over time. And distance is a measure of length, then time is a measure of time. So we can say that the dimension of velocity is what? Lt negative 1. So you're going to write this way. Instead of the all over sign, then you introduce a negative raised to power 1. 1 in the sign because we just have t, 1t. The power of t here is 1, so we can just write it linearly and then introduce negative to represent the all over. So the dimension of velocity is Lt raised to power negative 1. So you can see how velocity is related to length and time. Then that is velocity. So similarly, speed, whether velocity or speed, they are mathematically the same. The only difference is that a velocity is a speed measured in a given direction. You understand? A specified direction or in a particular direction. Then this has been treated. So we talk about acceleration. So acceleration A is the velocity over time. So already velocity has been found to be Lt raised to power negative 1. Then over time, dimension of time is t. So meaning the dimension of acceleration will be what? Lt negative 1. Then bringing this one up, negative 1. So meaning you have Lt negative 2 raised to power negative 2. So that's the dimension. This is the dimension of acceleration. Lt raised to power negative 2. So that is taken for acceleration. So we cannot say acceleration is related to length and time by this. So it's a length divided by the square of time, because explain it like that. Then we go to the next. So treated also is acceleration. Then let's look at force. So we define force. We say force is the product of mass and acceleration. So mass is a measure of mass. It's a fundamental quantity itself with dimension m, capital M. Then acceleration, we just find it to be Lt raised to power negative 2. So meaning the dimension of force is m Lt raised to power negative 2. So we can see how force is related to mass, length, and time. So take note of that. Then we look at energy. Energy and work are the same. Understand? So mathematically, then energy, whether energy or work. So usually we define work as what? Force times distance. Yes, sir. So mind you, distance is s. The symbol of distance is s. So force force times distance gives us what? It gives us work. So and force, the dimension of force is already found to be mlt raised to the power negative 2. You understand? So mlt raised to the power negative 2. Then multiply by distance is a measure of length. So meaning the dimension of work or energy is what? M, then L times L square, and then T negative 2. So that is the dimension of work or energy. So you can see how work or energy is related to mass, length, and time. I hope just this understood. Then we treat, let's say, pressure. Pressure. So by definition of pressure, pressure is what? Force over area over area. So the force exerted on a unit area is what we call the pressure. So like when I'm standing, I have a force. My weight is my force. So I'm standing on a surface on a certain area. So if you want to measure, if you divide my weight by the area I'm standing upon, that is the pressure. So the force you feel on a unit, area is the pressure. So dimensionally, force has been given as mlt negative 2 because it is the product of the mass and the acceleration. So this is force. Then area, the dimension of area is L square. So what happen now? Then one L is gonna cancel one L. Then you'll be left with M and a length under. A length under will come up as L negative 1. Then you have this. So this is the dimension of pressure. So pressure treated. And let's look at power. So power, so they will tell you power is the rate of doing work or the rate of dissipation of energy. So what does that mean? So it means power is work or energy all over time. So that is what it simply means. That is power. So and already work, the dimension of work has been found because work is force times area. Sorry, force times distance is work. Then all over time. Force times distance all over time. So our force is ml negative 2. Is that how it was? ml t negative 2. Then our distance is L. Then our time is T. So meaning you're going to have m L times L square. Then T raised to the power negative 3. T negative 2 here. If negative 1 is coming, it becomes negative 0. So ml2 T raised to the power negative 3 is the dimension of power, which can simply be seen. And I think when we say work was ml t negative 2, then multiplied by length ml squared t negative 2. That was first ml squared t negative 2. Then divided by time, then you're going to have ml2 t negative 3. So that is power. So I think with this we can say we have three.